So I've never had to listen to one lecture for 3 lectures in one day, so I can't imagine what it's going to be like. I have Philippe isn't here. I have a shorter set of slides, so unless Philippe walks in the door, I might stop slightly before the hour is up. But I will switch on the problems at the end, because if there are people who like playing with GAP, I'm more than delighted and excited to kind of press buttons. So anyway. So this morning, I hope, was I explained how one can, or various ways to represent a topological space on the computer. And I hope I got across the idea that homotopies are useful in doing calculations. And I illustrated the type of calculations by doing some cohomology or homology calculations, homology of groups. So this, when Philippe said talk about topological methods, I wasn't quite sure what to talk about, but this this workshop is the title is Cogent, Cohomology, Geometry, a number theory, but the geometry, you know, so I thought then something about 3 manifolds would fit in. Also, Kelvin, who is finished more or less his PhD, has recently been implementing things on 3 manifolds. So I just thought I would talk about that. Just an example of you know, how it is a convenient environment to implement topology, how GAP is a convenient environment. Okay, 3 manifolds. What am I going to say? Switch it on maybe. Yeah. Okay, so I talked about biology and knots this morning, so I've got knots out of the way. And there's a celebrated theorem, the Licorice, proved independently by Licorice and Wallace many years ago, which says that any closed orientable 3 manifold, so we won't look at non-orientable manifolds, any closed orientable 3 manifold can be constructed by performing Dehn surgery on a link or a knot or a link in the 3-sphere. So this morning I was taking a cube, you know, a box of 3 space, but I suppose strictly speaking you should take the 3-sphere. Anyway, that's this theorem. So from Christmas time, Kelvin says, wouldn't it be fun to implement this in GAP and try calculating cohomology rings and so on of 3 manifolds using this theorem. So I'm going to, in the talk, and one, because I don't lose anything by talking about knots really, but also we've only implemented it so far for knots, so there's some more implementation needed for links. I'm going to focus on knots, by which I mean an embedding of the circle S1 into 3-dimensional space of the 3-sphere. So I have to say what Dehn surgery is. Well, maybe before I say what Dehn surgery is, I have to explain a kind of an efficient way of producing for a knot complement a CW structure, a regular CW structure on a knot complement. So that's what I'm going to start off talking about. So knots are often given in terms of planar diagrams, knot diagrams. So here again is the trefoil knot. Well, at least that's a planar diagram of the trefoil knot. And we'd like to construct, in a reasonably efficient way, not too many cells, a regular CW decomposition of the complement of that knot in the 3-sphere. So one way to do it is to, first of all, from your knot diagram, close up the underpassings, overpassings, and consider this second diagram in the disk D2. So that's a diagram in the disk D2. And then let's give this disk D2 a regular CW decomposition. So there we have it. I've chosen various 0 cells, and then the various 1 cells, you can see there. And then I suppose we filled in the patches, various 2 cells. And so what you see there, I hope, is a regular CW decomposition of the 2-dimensional disk, which is in some way associated with the knot diagram for the trefoil knot. Then what do we want to do? We want to construct a knot. So I think this picture hopefully is kind of self-explanatory. We want to put back in the under and over crossings, and the 0 cells have been chosen either side of, let's have a and this undercrossing here is going across. So we've added in a vertex, and a vertex, so on. And now what we do is simply lift. So we take the direct product of our disk with the unit interval, so you get a solid cylinder, and then you just lift up the overcrossings. And what you get, hopefully, is something that looks like a curve, an embedding of the circle into the 3-dimensional solid cylinder. And I suppose we also need to, well, yeah, so that's a solid cylinder, and I suppose we need to add on a top and a bottom. Maybe we could add on a solid hemisphere on the top and a solid hemisphere on the bottom, and then we'd have a knot inside 3 space. And then what you have to do, well, you just have to remove an open tubular neighborhood of this knot, and that will give us the complement, which would be a regular CW structure on the complement. Just before the talk, I felt it's maybe worth saying a little bit, because to actually implement this, in quotes, remove an open tubular neighborhood takes a fair amount of work. So let me say a little bit about the algorithm for removing a neighborhood. So the algorithm basically, if you have a CW space, a regular CW space, and you have a subspace, a regular, a CW subspace, we'd like to somehow take an open tubular neighborhood of the subspace and then excise it, take it out, remove it. So the algorithm, it's a bit more fiddly than this picture suggests, but I think the picture gets over the essence of the algorithm. It's as simple as this. So here, forget the dotted region for the moment. I've shown a CW decomposition of some planar region. And now I'd maybe like to remove an open tubular neighborhood of this thick black CW subcomplex involving 3 0 cells and 2 1 cells. So the thing dotted is the open tubular neighborhood. And you can kind of see what you have to do. You have to just say, like, you cut it out and add in pieces to get the complement. Now, I know there's a bit more to it than that, but I'm not going to go into the details. And so that is actually, by Kelvin, that's implemented in GAP now. So given a CW space and a CW subspace, there is an implementation of an algorithm which removes an open tubular neighborhood of the subspace, and so you're left. So one way or another, we can get complements of knots. Okay, so what's Dane's surgery? So Dane's surgery then is we construct a manifold, a 3-dimensional manifold as follows. So you choose your favorite knot, K, or link, but I'm going to stick to the knot. You choose your favorite knot, K, and you take the complement of an open tubular neighborhood of K from the 3-sphere. So I suppose this is, I'm removing K, so I'm looking at the complement. And so I'm thinking of K as maybe being like this morning, a thickened knot, an open thickened knot. So I remove it. And then what I've taken out is a solid torus. And now we just glue in a solid torus. Glue back in what you've removed. But when you're gluing it back in, we'll do something fancy. We'll take a homeomorphism. The boundary of the torus is a regular hollow torus. We'll take a homeomorphism from the boundary to itself. So so that kind of changes the space. This homeomorphism. Yeah, so the boundary of what I've removed is going to be the same as the boundary of the complement, and then I glue back in what we've removed, but using this homeomorphism. And again, it's a bit fiddly to do in the category of regular CW complexes, but it is doable. Okay, so you just have to take the trouble to write the code, and that is now implemented. So let's have a look at an example. So you might, so I guess in orange, I have the boundary of the knot. In this case, I've taken the trivial knot, so it's just a circle embedded trivially in 3 space. So the orange thing is, if you like, the boundary. And then we can think of the surface here, the surface of this torus, or the torus, as being determined by a meridian path and a longitude. And then what does the homeomorphism do? Well, really a homeomorphism can be specified by saying, what does this longitude get mapped to? So in this example, picture produced by Kelvin, we could map the longitude, we could wrap it around, I think it's 17 times one way and 3 times the other way. And so we map the longitude. We capture this mapping by 2 numbers. Yeah, so I wrote it on there. H, this particular homeomorphism I'm illustrating, is determined by the image of L. L wraps 17 times meridianally and 7 times longitudinally. So we can determine a torus like that, a homeomorphism, and now it's just a case of gluing back what we've removed, but you have to constrain yourself. You have to work in the category of regular CW complexes, so it's a bit fussy. I won't go into the details, but it's not deep mathematics. Okay, so that's what Dane surgery would be. And then you record the Dane surgery. You say, in this example, we've gone 17 times and 7 times, so there's a P over Q is the Dane surgery coefficient. It's P over Q, 7 over 17. So if you have a knot and a P and a Q, you can do a Dane surgery. Yeah, so that's just repeating what I said. I mean, really, we can only store on the computer regular CW complexes together with contracting homotopies, but still you have to have the regular CW complex. And in terms of maps, topological maps, the only thing that's easy to store are inclusion maps of CW complexes and also projections, but I'm not using projections here. But working in this category of regular CW complexes and cellular inclusion maps, you perform that construction. So you have to take mapping cylinders and all the rest and make it work. So let me just say a little bit about certain kind of manifold that people look at, and then I'm only going to look at a special type. So a Seifert manifold then is a 3-manifold M, which fits into a fibration sequence where the fibers are all circles. And I think you can probably take any surface here, and if you take the surface of genus 0, I suppose it's a genus 0 Seifert manifold. So that's what we were interested in playing with to see how this works in GAP. So how do you represent that using Dane surgery? So it turns out that well, okay, in general, now I'm backtracking. In general, you would use links. You can do Dane surgery just not with knots, but with links. So what I've drawn here is in black is a link. And so a Seifert manifold can be represented in terms of Dane surgery as taking the trivial knot and then linking it with several trivial knots. And then on each knot, removing a torus and gluing back a torus using various Dane surgery coefficients. And if you do that, you'll produce a space, which is a manifold, which is called, well, I'm going to call it L of P, Q, P1, and so on. So that's what a Seifert manifold is. And there are some papers calculating cohomology rings of Seifert manifolds and so on. So we thought it would be good to see, is this doable in GAP? And I'm going to focus on the special case because historically this special case has been of interest. I'm going to talk about lens spaces. So a lens space is the easy case where we just have a trivial knot and no links. And you just take a P and a Q. So a lens space, one definition, is that you take your three-dimensional sphere, you remove the trivial knot, and then you glue back in what you've removed, the torus, using PQ coefficient. But of course you could do it with any knot, but the lens space is the trivial knot. So I just mentioned some papers, Zishang and others, quite a few papers. Yep. Yeah, I'll do it again. Yeah. I didn't really say so. I said that in this case, P was 7 and Q was 17. It's the number of times you wrap around, and I'm forever getting confused between what's a meridian and what's a longitude, but I hope I got it right there. So the P and the Q, the P and the Q are the numbers that determine the homeomorphism. Yeah. So Zishang and others have written quite a few papers on calculating cohomology rings for Seifert manifolds. And going back to history, lens spaces were interesting in that well, at least is it possible to classify up to homotopy lens spaces, and that's something that Henry Whitehead did, and he used something which I will describe, the linking form, to do it. And again, all these things, the point I'm trying to get across is that they're quite easy to implement in any computer system, and such as GAP. And then more difficult is classifying lens spaces up to homeomorphism. So Reidemeister classified lens spaces up to piecewise linear, and then Moyes, classified them up to homeomorphism. But Moyes' proof used the Hauptvermutung, which is, I guess, that the belief that any two triangulations of a manifold, if you have one manifold and two triangulations, you can subdivide each of the triangulations so that eventually you get a common subdivision. And the Hauptvermutung is false in higher dimensions, but it is true in dimension 3. And so the invariants here used were Reidemeister torsion and various variants on it. And so it's kind of fun to see how these kinds of things can be calculated in GAP. And then a point that I'll talk about later is that cup products and needed in the above. So if for no other reason, this is a good motivation for why I should talk about cup products, because this here is essentially a cup product. So there's a gap session, which I'm going to try. Gap session number 4. So let me do it slowly. We've seen this command this morning, but I'm repeating it. I'm just well, okay, it's a different picture, but that's a picture of the knot, the knot, the first knot on 3 crossings, the first prime knot on 3 crossings. It's the trefoil knot, and that's another picture of it. But this is a handy enough picture because if you want to encode knots, this kind of diagram, which are called arc presentations, where the overcrossings are all downward sections and the undercrossings are horizontal, it's easy to encode with a numerical invariant. So that's a picture of this trefoil knot again. The next command I will try is, I will, not that it means too much, but I will produce from it a numerical description, which I call arc presentation. So from that trefoil knot, we have the arc presentation, which I probably will get wrong now. So we have, let me get it right, we've got 1, 2, 3, 4, 5. In fact, the best way I can do it is to draw the picture up again so that I don't go wrong. Let me, no, this is the cog note. So let me have a look. See, so maybe I just point. 2 to 5. So I'm not, which way am I working? I'm working from bottom up, I guess. So I reckon that the bottom line starts in the second column. I'm thinking of 1 column, 1, 2, 3, 4, 5 columns. So the bottom line starts in the second column and ends in the 5th column. Then I move 1 up. The next line should start in the 1st column, I've got it, and ends in the 3rd column. And then the next line should start in the 2nd column and end in the 4th. The next one starts in the 3rd column and ends in the 5th, and so on. So you can capture, you can describe knots using this arc presentation language. So what do we want to do? I want to construct, now I'm not using the trivial knot, I'm using the trefoil knot, a 3-manifold. Using Dane's surgery. So it's thinking, but okay, what's it done? Well, maybe if you use a single semicolon, you get to see what was produced. It's produced a regular CW complex of dimension 3, but that is a CW decomposition of the 3-manifold. Let me whiz through all of the commands. Now I do something that really is not satisfactory. I'm going to take the barycentric subdivision of that regular CW complex. The reason I'm taking the barycentric subdivision is that there's some mathematics and some implementation that needs to be done. But for simplicial complexes, many constructions are easy. For regular CW complexes, you have to think. So I've produced a simplicial complex, homeomorphic to the manifold. So it's a and then what's the next command? I'm going to, you can read them here. I'm going to do all of these at once. I'm going to construct the cohomology ring. I'll talk more about that in a moment, but on cohomology, there's a ring structure, product structure, so you can construct a ring. GAP has an environment for working with algebras and so on, so it's grand to implement there. And so it's a ring with a finite basis. I'll take a canonical basis, and then I'll print out the multiplication table for the generators, and we'll see what we get. I mean, it won't be anything too exciting, but I'll do all of this. And this will only work at present for simplicial complexes. And so you get the multiplication table for the ring, which is the kind of thing that these papers on cohomology rings were after. Now you can only do one example at a time. I mean, obviously, theoretically, you can prove theorems. And the bad feature of this is that if you take any reasonable size manifold W, the barycentric subdivision will be so big that the example won't work, so more work is needed there. Let me just go on to see what I can illustrate. We might want the so I can just read it. We might want to construct the universal cover of our space. We've got the space W is the 3 manifold. So you might want to construct the universal cover. So the universal cover will also be, well, it'll be a 3 manifold. And of course, it could be, I mean, your fundamental group could be infinite. So it had better be stored not as a CW complex, but as an equivariant CW complex, like we had this morning, the torus. So let's construct the universal cover. U for universal cover, and I'll also take G as the fundamental group in these commands. So let me illustrate that. Okay, so I've constructed the universal cover U. We're lucky in that the fundamental group, which is associated to the group of deck transformations, we're lucky that it's finite of order 48. So we have a group of order 48. And then what else can we do? Well, because the fundamental group is finite, it is possible to represent U not as an equivariant not only as an equivariant CW complex, but actually as a regular CW complex, because it's a finite fundamental group. So let's just do that. I won't explain in detail the commands, but you get the gist. So it's thinking, and it's produced a regular CW complex. So this is the universal cover. What could you do? Well, you could ask for the critical cells of the universal cover, because that'll tell us, it'll at least be smaller. So let's look at the critical cells. There are only 2 critical cells. One critical cell has dimension 0. It's of all the vertices, vertex 642 is deemed to be critical. There seem to be no 1 or 2 dimensional critical cells, and there's a 3-dimensional critical cell. So this universal cover, you have 1 3 cell, 1 0 cell. It has to be a 3-sphere. So that shows that it's a 3-sphere, and I think that's that example. Have I covered all the commands? Well, no, I can go further. I talked about lens spaces. So lens spaces, we don't need the trefoil note. We just need a simple note. So let me construct. Let me first of all construct. Maybe I won't do that because I haven't said what the linking form is. It doesn't make sense. So let me go back to the slides. I'll do that later. Okay, so that was the session, except I stopped when I started using cup products and linking forms because I wanted to say something about cup products. Okay, so what's the cup product? So I guess it's easy to define. It's only when you come to put it on a computer that you have to think about the definition. But so if you take any space X, you've always got the diagonal map from X to the direct product of X with itself, which sends a point lowercase x to the pair XX. This is the diagonal map, always defined. And then if you're doing theoretical algebraic topology, you'll then know that any map can be approximated by a cellular map, and a cellular map induces a map on homology or cohomology. So, well, cohomology is contravariant. So this diagonal map here induces a cohomology map. And then it's not hard to see that when you're looking at the cohomology of a direct product, there's a fairly canonical way to embed a two-tuple consisting of something from the p-dimensional cohomology of X and the q-dimensional cohomology of X. I think it's the cross product will give you something in the n-dimensional cohomology when p plus q equals n. So this here is just read Alan Hatcher or Spanier or whatever book you want and implement it. But this here, one has to think a little bit about how to do it, because the diagonal map is not cellular. So the diagonal map typically will not send a one cell to a one cell or a two cell. And on the computer, working with regular CW complexes, when you have non-cellular constructions, you have to fight to make them up to homotopy cellular. Okay, so if, there's an example then of a case where I've taken the space X to be the unit interval involving two vertices and one edge drawn in black. So that's the space X. This in black is the unit square, X, direct product X. And then the image of the diagonal map is this line, which is not cellular in the sense that this orange image is not a one cell. And it's not even a union of one. It's not even a union of one cells. Yeah, we don't need the details. So let me introduce the definition of a diagonal approximation, because it's a diagonal approximation is what you need if you want to implement this kind of thing. So a diagonal approximation is defined to be a cellular map. So cellular, I should have said, if you have a CW complex X, then you can talk of, so a CW complex you can think of as a partition of X into cells, the cells having various dimensions. So you can think of Xn as being the union of all the cells of dimension n or lower. Xn is the n skeleton. And so cellular, a map would be cellular. So a map F from a CW space X to a CW space Y is cellular if F of Xn lies inside Yn for all n. That's the definition of a cellular map. And then a diagonal approximation is a cellular map, capital D, from X to X cross X, with the approximation has to be homotopic to the diagonal, and you'd better insist that when you restrict to the zero skeleton, the collection of vertices, it actually agrees exactly with the actual diagonal. Yeah, so that's a diagonal approximation. And if you want to implement cup products, you need to think about how to implement diagonal approximations. So the easy way to do it, but not such a great way, is to say, well, Alexander Whitney solved this problem for simplicial complexes, so we can just Google the Wikipedia and implement the Wikipedia for simplicial complexes, and then only ever apply it to simplicial manifolds, which is what I did there. So I took a manifold, took its barycentric subdivision, and then used the cellular map. Oh, I've explained what cellular means there. Okay. So so let me just say then what the Alexander-Whitney theorem tells us, or construction tells us. So if you have a simplicial complex X, so a simplicial, for me, I'm thinking of ordered simplicial complex. So there's an ordering on the vertices, and then a simplex is an n-tuple, of distinct vertices. You can define a front I face and a back I face as follows. So if you have an I simplex, an I-dimensional simplex, you can define its front face. Let me have a look. Sorry, I'm getting confused. If you have a k-dimensional simplex, sigma, you can define its front I face to be the I simplex got by just forgetting everything after position I. And you can define the back I face to be, sorry, I've got it the wrong way around. The front I face is everything, you forget everything, you forget everything after position I, and the back I face is you forget everything before position k minus I. Yes? So there are these two constructions, front face and back face, and then the Alexander-Whitney diagonal approximation, you can Google the Wikipedia for this, is the cellular map. Well, I'll tell you what the image is, because it's easier to say what the image is. The image of a simplex, or a cell, sigma, is just the union over all I plus, I guess I'm taking a k simplex, is the union over all I plus j equal to k of the front I face direct product, the back j face. I think I have a picture. Okay, so if you take k equal to 1, what I have here is a 1 simplex. It's a two-tuple of distinct vertices, v0, v1, and then the diagonal, the Alexander-Whitney cellular approximation is the union of this simplex, which is this vertex, direct product, the 1 simplex, union this one cell, which is the 1 simplex direct product v1. Because remember, we're working in the direct product, so here we've got pairs. Maybe actually k equal to 2 is more informative. If you take a 2 simplex, what does the Alexander-Whitney diagonal approximation look like? Well, the image is the union of the vertex v0 direct product, the 2 simplex sigma here, with sigma direct product the vertex v2 here, and this 1 simplex v0 v1 direct product this 1 simplex v1 v2, which is this square parallelogram here. And I remember, so I do know that k equals 3 is down. That's the picture of k equals 3. So the diagonal approximation for k equal to 3, if you take a random simplex, its image will be a union, again, it'll be a union of this simplex, it'll be the vertex direct product, the 3 simplex here, and the top 3 simplex, so it's the 3 simplex direct product, this vertex, together with some prisms. You've got this 2 simplex direct product this edge, so you've got a 2 simplex direct product an edge, a Toblerone. You eat Toblerone in France? Yeah, okay. I wasn't sure. You've got a Toblerone, and then there's another Toblerone cell there. Okay, so that's, and then I can't draw any higher, but at least there's a formula, so that's easy enough to implement on the computer, and you can produce cup products. So let me see what the, gosh, I said I was going to stop it. Okay, so I said that already. Currently, the implementation is poor because given if you want to find the cohomology ring of the torus, the current procedure would be subdivide to produce a simplicia, a triangle, a horrible triangle. It gives you a cellular, it gives you a cellular approximation. Yeah. It does. It just by just the formula. I mean, I gave you the image, but yeah, you get that. Yeah. Just that's. But it's not a great way to do it because the barycentric subdivision is rather large. And in fact, even in the current implementation, it's not quite as naive as working with simplicial complexes because they are very big. So in the background, if you have a very large cellular space, very large simplicial complex, in the background there are lots of discrete vector fields being calculated, and you produce a small non-regular CW complex. When you actually do calculations of homology or cohomology, this yoke here is what you're really working with. But to understand everything theoretically, you have to record the chain homotopy equivalences forwards and backwards, and then you use the left-hand side, the very large left-hand side for theoretical formulae like the Alexander-Whitney product from the Wikipedia is working here, but when you calculate Smith normal form and do explicit calculations, you do it on the small space. And let me zoom on very quickly. Okay, so in lower dimensions, I won't say too much about this, but well, in dimension 2, there is an efficient method in GAP already, and I won't say too much about it, other than I think this picture kind of explains it. If you want to map a cellular, if you want to find a cellular decomposition, suppose you have a simplicial complex where you've got hexagons and you might be a Coxeter polytope or something, and you've got hexagons and prisms and so on, and you want a cellular decomposition. Well, in degree 2, what you can do is, what does this get mapped to? It's going to get mapped to something inside the direct product of x cross x. And just as with the Alexander-Whitney, you have a vertex direct product, the cell, and another cell direct product, the vertex, and then you have a rake of prisms, lower dimensional. And in the two-dimensional case, the prisms will all be an edge, direct product and edge, so they'll all be squares. So in fact, you can do this using commutator calculations with finite presentations of groups, so you don't need to think too hard. And so for the cup product from degree 1 to degree 2, this is the way that it's done. But in general, we'd like to think hard about cellular approximations. GAP session 5, but I will go on to 5. I'll go on to 5. Where have I gone? Well, I should stop kind of soon, isn't it? But I won't go on too long anyway, because it's time. Yeah, I get more and more excited as the talk goes on, but I can see. So hang on. Let's have a look. So let me skip that about lens spaces, because I haven't really said what linking forms are. But let me... Herbert isn't here, but he was interested in reflections of the trefoil knot and so on. And this is a long calculation, which might be due to my GAP programming, or it might be due to something theoretical. Let's go back to knots. I'm trying to illustrate cup products. So what I've taken there is the trefoil knot. And I've also reflected the trefoil knot. So we have the two, I drew it this morning, you know, there's a trefoil knot and its reflection. Now what we can do is we can construct two knots. So I can ask, what is the French for these? Does anybody know? Let me go down. The granny knot, the reef knot, the square knot. I don't know. Anyway, but there are two knots in English. Anyway, some people call them the granny and the reef, and so one is the. Oh yeah, you can add knots. So if I have a knot and I have another knot in three-dimensional space, and you have to be a little bit careful with orientation, but you could just break that knot anywhere and join in a, so if they're oriented in a consistent way, you can join like this and back, and you have a sum of knots. So that's what I've done there, sum two knots in two different ways. So we've got two knots, and it's known that if you take the complement of those two knots, they have the same fundamental group. So are they the same knots, or are they different knots? Can we find an invariant that distinguishes between them? So there are, I think, many ways to do it, but I just want to show one way. I've forgotten, it's here, is it? Yeah. OK, I'll view the two to see, can you just spot, even if, because some of these examples you can spot without knowing any mathematics. Can we spot that these two knots are actually different? So that's the granny knot. So I don't know how to, now it's your point, I don't know how to, that's the granny knot. Can I also produce the, yeah, I don't think I can produce the next, no, I have to kill it. OK, I'm going to have to kill that one to get the next knot. Yeah, I should have. OK, I can't have the two side by side so easy. But it's to tell if these two knots are actually different. Is it, how can we prove that you can't deform one knot into the other? So let's go on. And let's compute something, and I try to remember what it's being computed. So we take the arc presentation of the granny, because to any knot you can represent it with an arc by an arc presentation, an arc presentation of the reef, and then you produce the knot complement in S3 with the boundary. So you'll have two inclusions, FG and FR are two cellular inclusions of the knots, the circle, into the three sphere. This is the bit that I have to explain, but as it takes a while to calculate, I'll have time to explain. And then this is more or less where I stop, but I have to explain what these commands do. So I'm calculating something there. What am I calculating? So for the first knot, the granny, we have the knot, and we have the space, let's call the space X to be, or S3 minus the granny. So that's the space X. Then I can look at finite covers of this space, finite covering maps. Yep. And the 6 here, oh, I better press return. I don't know what happened. I have to press return. I take I take all the 6-fold covering maps that I can find, because covering maps correspond to subgroups of finite index 6 in the fundamental group. So we've just heard about that kind of calculation. So I take all the 6-fold covers. I don't know what to call them. Six-fold covers onto X, but all of them. And then for each cover, I'll look at the first homology which we use Smith normal form and probably discrete vector fields and everything to calculate, and we'll get a list of numbers. And if you think about it, if there were a homeomorphism, this is for the granny, and if y was the equivalent thing for the reef knot, if there were a homeomorphism, so I can say two knots are equivalent if there's an orientation preserving homeomorphism from their complements. I should have said that. So if there were an orientation preserving homeomorphism, what you would find is that this construction would be the same for both knots. So what we've produced is that two lists, and I've ordered them because I don't know which, I don't know which order I've produced all of these 6-fold covers. So we sort things in gap, so that and then we just ask, is A equal to B? And if A is not equal to B, the granny is not ambient homotopic isotopic to the reef knot. So you say A equal to B, and it's not. And if you want to see what A is, A will be a list of lists. Each list will be the list of being invariants of the first homology. Well, that was A, and B was a kind of a long knot. Okay, so I won't. I won't talk because it's late. Okay, I won't talk about the linking form. They're in the slides, which are on the web. But if you want to go back to manifolds, and if you want to distinguish between the homotopy class of manifolds, you need to use the linking form. It's defined in the slides, which are up on the web. I won't read through them, or maybe I'll do it next time. But it uses the cup product. And if you want to distinguish between the homeomorphism classes of three manifolds, maybe I will say something about that next time. Again, you can use a version of the cup product if you're very careful, a tweak on Reidemeister torsion. So maybe I'll postpone that to the next lecture, and I'll stop there. And thanks for listening to me 3 times. I don't think that's ever happened before in my career. Okay.